Transform Infrared Spectroscopy and high-level Raman Spectroscopy to confirm the electrode surface interactions. She has received more than 1 million as funding for research, and this is very impressive. And we have here a high-level speaker. Susan, welcome to your talk.
Thank you very much. Well, today what I'm going to focus on is some real hands-on workshops which I have developed to help teachers take back to their own students in their own classrooms. And so that's why the title is Multidisciplinary, because I'm going to show how to integrate math and science like physics, geology, biology, and chemistry with electrochemistry, even in some aspects as well, in inquiry-based learning. And so I'm at Wright State University, and what I'm trying to do is also integrate with industry, because we know hands-on aspects, working with industry is very vital to encourage teachers and our own students in the K through 12 school districts to really see how it relates to our everyday problems and what we're trying to solve in the real world. So as global citizens, I have a lot of slides today, so please bear with me. I'm trying to keep you awake. But we know we need to know why we're doing something. Obviously, the biggest thing I think with schools, they need to be structured because students need to be engaged in a process in which they understand and they see where the real world problem is bothering them and how they can really help their own students see. State exams are not really doing that. They're not allowing you to see the real world issues, and that's what we're trying to do. Why are we solving a problem, and how does it relate to our industry and our real problems as when we go out in the world to get a job? So lives engaged in industrial problems, this has been cited by sources in Orozco and Satin in 2007. I've reworded it, but this was one of their addresses, was talking about how do we engage students in learning. So a lot of times through here, I'm going to be citing literature to just confirm why I did things that I did, to see why I think it works. For me, that doesn't mean there's other ways, like Dr. Blair the other day did a great seminar on engaging, and today I'll talk about how I also do some online aspects within that to follow up, because I think you have to have various phases, not just hands-on, but also online learning can be very vital as well to continue the process. So STEM, science, technology, engineering, and math is where we're structuring. In the United States, we need to gain more science and engineering majors. And so our focus is how do we do that? How do we get United States to stay in the science field? Because now what we're having as problems is we're having to hire people overseas because we don't have enough scientists, or students are failing in math. So how can we create these structured experiences, real world issues, and also resolving real research problems? And today I'm going to show you how Bowser-Morner and CEMEX and some quarries in Columbus, Ohio have come together with me to get real world industry involved. There's obviously a relationship between content and process. So these arrows are just saying that you have to have content and you have to have process. And that really helps focus when you're putting a lesson plan together. What is the content you're trying to hit? And what is the process that they're supposed to come up with to make sense of real life experiences? In any inquiry-based lesson, I feel that you should address these issues. So Wang in 2003 with Wilson talked about integrated curriculum is best delivered in an inquiry approach. An inquiry approach allows you to be more powerful in terms of how you get the content out to your students, and they're engaging and they're solving the problem on their own. So they're actually becoming their own research-based scientists to engage in the process. And as you engage in the process, it's just not memorizing, because memorization doesn't really help you learn. You will walk away and forget it. But if you're actually engaged in the process, you're going to remember it. Also, Betancourt in 1991 pointed out that discovery-based learning has been really proven to be very well. And I'll show you an assessment technique that I use by R.R. Hakey, pre- and post-test assessment, to look at content gains, to see if your students are doing better in a lecture mode versus an inquiry-based mode. Also, J.W. Lehman in the National Center for Cross-Disciplinary talked about the same concepts, that valid is the sense of describing the world well, and powerful in the sense of being useful, reliable for students in many diverse settings. So how do we engage all our students? You know, if you stand up today, I know it's kind of boring. I wanted to give you a hands-on activity. Dr. Blair and I talked about that. If there was a way we could, at the end of each session, give you an activity and really make you solve it and see that that works better than just standing up here and lecturing. Because we know that once you do the hands-on activity and you resolve the problem yourself, you understand the formula, the derivation better, and why it came to the final answer that you came with. So traditional learning is how we typically present, especially to large lecture halls. You have 200 kids in a lecture hall, and they're really not getting it. That's why half of them skip class, because it's boring. But what we've tried to do at Wright State University is create an inquiry-based learning environment where we break our class for the inquiry-based learning for our science educators into a maximum of 24 students. So they're required to work in groups and get this hands-on activity. Also in our MST program, Master of Science in Teaching, we have smaller units. At most, in some of our grad programs, we maybe have 15, again, to 30 in a classroom, because we want to make sure they're getting that hands-on interaction, just not a lecture where they're going and memorizing. So in inquiry, obviously, the students have to investigate it themselves, where in traditional, it's just show and tell. Obviously, in traditional, the teacher's centered, and in inquiry, the student's centered, and the problems are centered around with the group. So we go around and we facilitate each group. The class structure, obviously, best for inquiry is a small class size, because 200 to a lecture hall can be challenging. However, there are techniques when I teach a large lecture hall like Chem 2100, our pre-meds, or our engineering majors. We used to have engineering and pre-med mixed together about 4 years ago. And when I engaged in that process, I would still put them in groups and have seats set up, so I do have 4 sitting close, and then divide, and then 4, and then I would give them a question and have them resolve the question and then discuss it, and then you can use clickers sometimes in that format to engage the students if you have a large lecture hall. But the smaller works well for us at Wright State, and these are the class structures. Obviously, assessment's very vital. How do you assess your students to make sure they're really learning what you expect? Assessment's a vital part. Dr. Blair was saying that today. If she doesn't assess her students, how does she know what they're doing online? So in keeping a constant assessment is very vital in our curriculum. And experience in the real world. So I'm going to talk about some modules that I've used for the K through 12 setting for our MST program. And then I'm also going to show you some modules that I developed just for even just chemistry majors. How do we relate to real world issues to create sensors for water quality contamination? Because everybody knows we don't want lead in our water or any dangerous heavy metals. So in the 21st century, what you have is typically this is what we're looking for. But the problem is we're not putting out critical thinkers. And so when our students go and apply for a job, they're not becoming critical thinkers, so they can't think for themselves. So they get a test from, say, P&G, Procter & Gamble in our area in Cincinnati, Ohio. And they fail the test. And the reason they fail this test is because when we produce them at the University Lecture Hall of 200, we're not really making them think and develop modules on their own and work in research-based kind of content. So how do we do that? How do we prepare students to pass and assess and get jobs? And so we want to create critical thinking, and I'm going to show you this module, how we've engaged with industry to create in a first grade level even an inquiry-based mode where they're required to critical think and solve a problem. So in inquiry, we're asking questions, we're planning and conducting investigations throughout, we're gathering data, we're thinking logically about the evidence, explaining through technology. Technology is a vital part. Later on, I will talk about once you put the technology in the hands-on aspect of doing the instrumentation, for instance, you should have the students using different types of software. I think Origin, Excel, all are different types of software. Later today, Dr. Najib with me, Dr. Basil Na is going to be working with me to talk about Excel and how we use graphing as a tool to enhance our content knowledge in our classrooms so our students can analyze data. But also, I'll show you today, not only just graphing by a computer, but also graphing by hand is very important. We have teachers, when they come to workshops and they're teaching in the K through 12, some of them can't even understand the graphing distribution by hand before we actually start plotting it with higher technology. So it's very important to include both of these. Communicating scientific arguments. We know that writing is a vital part. A lot of people forget that communication in the real world, when you go to take a test, you need to be able to communicate and write. All of us, in industry, or most of us are faculty, that we require to write, publish, or perish. But a lot of our students really do not have writing skills. So what I try to do in the early years is create modules. And as we create modules in inquiry-based units, we try to get our students to write their thoughts down, and not in a typical lab report format as well. I want them to keep a lab notebook, and it can be sloppy as can be, and then come up with the final format. So it's keeping an everyday process is important too. Keeping a lab notebook and analyzing at the end of the session, what have you learned and how did you put all your final formulation together with your lab report that you're coming up with. So it's just not just saying you have to have a lab notebook. I think a lot of faculty now are forgetting that very important part. And you can also do computer lab notebooks as well with the new software. P&G's making a lot of the industry do this, and so it's really good to enhance that once they learn how to do a typical lab notebook, once they get into higher tiered research, to actually do an online lab notebook. So Dr. Chile was very inspirational to me because he talked about, as a young scientist, you can read here, how he engaged as a young scientist, what we did as children. Why did we love science as children? And I think that's why a lot of people are drawn away from science now, is because they don't get to problem solve and see how much fun it is to investigate and resolve a problem. They're just memorizing a formula. And for instance, the Schrödinger equation is a great quantum mechanics theory, but how do you understand it? How do you relate it to it? How does it really talk to you about the potential energy and the kinetic energy? So how do we get our students involved in that process, not just memorizing, but role-playing and working through the equation? So there's 5 E's involved, and everybody knows in education pretty much the 5 E's. I also call it the 6 E's if you want to, because elaborating further is very important in my process to me when I put the students in a group. They wanted to engage, explore, explain, extend, evaluate, and elaborate upon the concepts. And so we must engage and have them engage in the process, and as they engage and explore, then they have to explain. That's the writing process. What was the data telling you, and what are you putting in your lab notebook? And then extending those concepts further, evaluating, and elaborating again together as a group. Because sometimes in experiments they don't work the first time. You have to try several reiterations until you come up with what is the problem and why isn't it working the way it should be. So inquiry is not step by step. And inquiry can be challenging at times because it is not step by steps, as well as in 2001 pointed out. However, it allows you to seriously investigate and rigorously understand the events as you go through the process, so you don't forget it. Because if you just memorize something, usually you walk out the door, you forget it. But if you actually go through the process, you're going to understand it better, and you're going to remember it, and you're going to be able to explain it to your colleagues better if they need help on that process as well. So what I've done in my inquiry units that I've developed, I worked on heavy metals, carcinogenic compounds, phenol contamination, something very important to learn how to detect, corrosion versus anti-corrosion. How do we learn, how can we prevent corrosion on products, and identify our actions as a community. So in STEM field, I think this is important to engage our students this way. Nicolas Sue talked about some very interesting aspects on transdisciplinary, which is inquiry-based learning as well, just in case you're reading the literature and you kind of want to see the gist between the inquiry-based and the transdisciplinary. They're saying the same things I am saying, that you have to learning to know, learning to do, learning to live together, and learning to be. It's a lifelong journey. We never stop learning. Even as professors, we know every day that if we aren't learning and engaging in the process, we're reading the literature, and then we might go in the lab and try something, and that doesn't quite just, so then we try something else, and then we read the literature again, and we keep reevaluating. We are never going to stop learning. Once you stop learning, it's pretty much the end of your life. So we want to make sure our students understand that asking questions and engaging is what we want them to do. We want them to continue the process and to formulate their own ideas as they go along, and then discuss it as a group. And if we have 6 groups, say, in that classroom of 24 students, 6 to 7 groups, they can work together too, and they can put their ideas together and formulate as well, and discuss the positives and negatives of their formulation of what they've derived. So what I've done here is I've worked collaboratively with a colleague in geology, and he is a geologist and I'm a chemist. And so one of the things we did for our MST program, Master Science in Teaching, we came up with a workshop for teachers. And in this workshop, we asked the teachers, and we had an interview, and I don't have time to show you some of the interviews, but they were really unique. We asked them, what is aggregate? What is aggregate? And they couldn't tell us. They came to our workshop, and they just knew that they were getting free graduate credits, so that's why they came. Yeah, they came because they were getting free graduate credits. So you have to have a little bit in your gut, like you said, to learn. Free graduate credits, just free credits. So to keep their license in teaching. So when they do that, to get free graduate credit, I don't know if it's going to fit. How about if I put it right there? Is that good? Okay, I'll stay still. So to get free graduate credit, this is the only way we can inspire them to come, basically. So they come and they say, okay, I get 3 free graduate credits for this summer workshop. And there's 3 parts, Dr. Blair, that was very, very extensive. We had phase 1 where they had to be in the summer field trip. And then phase 2 where they had to be online. And phase 3 they had to be online as well. Because what we have found is when we run workshops, anytime, I've been at Wright State for about 20 years, is that you'll run a summer workshop and it's not very successful because they don't continue the process. They just get the free credits and walk away. So the part of the bargaining part is to get the 3 credits, you have to do all 3 phases. You just don't walk away with 3 credit hours for free. Within that, what we have is we ask them some questions like, what is aggregate? Well, they don't know aggregate is sand and gravel and shale, things that we need to build buildings. Shale is for energy. So how do we teach them about petroleum, and they dig it up and they have shale down there, they have gravel. In the state of Ohio, the aggregate industry is a vital part for the economy because we have the quarries in Columbus, Ohio. So what's a better place to take a field trip than only about 45 to 50 miles from Wright State University? So we go to the quarries, and the question is how much, they don't know how much aggregate is in a box. We give them an unknown box. We take them to a quarry before we actually give them the unknown box, but we tell them we're going to give you an unknown box. And you have to figure out what is in that box. What is the percent of aggregate? Just like you would do in industry if you were digging out the ground. How much can you get out of that product to build a bridge or to pave your driveway or make something? How much aggregate are you going to get out of that? They don't know the topography of the bedrock. It's unknown. They mathematically have to figure out what is the topography of the bedrock. So obviously they know volume equals length times width times height. They can figure out the length of the box and the width of the box because it's a typical box that you put like copy paper in. Very, very easy project to do. Anybody can do this project. It's very simple. You just get a box, a copy box, and it's empty. And then what I do is I put plaster of Paris in it, and so each box has a different topography. So it depends. You'll see the different topography when I get at the end here of it. And they have to figure out, they don't see the topography because it's filled out with aggregate. It's just like what they're going to be doing in the real world. We go out to a site and we watch them drill, and we see how they drill the sites. So they have to figure out, they only get 5 straws because we tell them each drill's $1 million. We only have $5 million we can put in this project. So the height of the straws before drilling, they need to know the length and height so they know approximately what is the bedrock below and what is the area above of the top of the aggregate. So in order to solve this problem, they need to know the height of the aggregate level, and they also need to know the depth for all 5 straws that they are drilling. So they measure the length and width of the box. This is what this group did. There was various ways to do it. Some groups actually, after they measured the length and width, they actually drew pictures of what they thought the topography was after they put the straws on the outside of the box, which was very interesting. And they placed straws in the aggregate area, and so here is, they're putting a string across the box. So this is what the box looks like. And the reason it's white on the side of the box is because that was plaster of Paris to make the bedrock at the bottom. Here's the 5 straws. So again, we're doing cross sections. So mathematically, they have to figure out what is the amount of bedrock and what is the amount of aggregate in this project that they're going to come out with. So they start measuring, and that's what this talks about, the depths. And when they measure, pretty much, you can see what happens. They have the height of the aggregate and bedrock, the height of the aggregate, and the height of the bedrock. So they come up with the mathematical of the information. And then here's what they theoretically draw. They think this is what the aggregate looks like, and they think this is what the bedrock looks like underneath. Let's see how close they are. So they do the measurements. They get the centimeters cubed, length times width times height we talked about. I said, what would you do if you added 1 more straw? Obviously, that would change the measurements. Everyone agrees? So the placement of the straws is an important factor, Jeremy. Don't you agree? That's the key here, is that we're making them think. If you have a group that's not very with it and puts 5 straws along this way, we may never know what's going on this side, right? So we're trying to give them the real world sense. If they're going out on a job and they're working for Bowser-Morner Chemical Company, which they visit before they actually get this box, and they visit some quarries, they get to understand that where they put these drilling holes really have a factor on what is figuring out the area within that. So they were only 1.6% off, and I just want to show you, this is the box that was made, plaster of Paris. That's sand, a little bit of debris of sand that got in there. But you can see, they kind of were close, weren't they? Remember they had a peak like that? Yeah, so they were close. Not all groups were that close, of course, because I said it depends on how they put the straws, and that's the learning process. So the groups that really failed and had a higher percentage, they had to go back and figure out, give them a different box and do the process again. Because it's important to make sure you go through the process till you really understand it. And some students even seen there was other ways to figure out length times width times height in terms of measuring, like on the straws, like on the outside, how to do the box to get a better, closer measurement when they'd hit the bottom, how to kind of figure it out. So, you know, being reproducible results is important too in how you're measuring. So the conclusions within is they found that there was an effective way to take into account the surface topography as well as the bedrock underneath. That's what they learned that industry was doing. They also could figure out, obviously, the straws had a great impact where they put those, what I told you. So this was a good lesson plan because what they did is how much aggregate is in the box. They actually went through this and they have first grade standards. So these teachers were first grade teachers and they took this back to their classroom and they talked about how are they hitting the standards. The question is, how do we hit the standards, but we hit them as we're also addressing real world issues and problem-based knowledge that needs to be going on in the classroom? How do we integrate math and science and allow our students to problem-base? And so this curriculum has allowed it because they're doing scientific inquiry, they're hitting physical science, they're looking at physical properties, they are involved in earth science, and you can see also they're working in small groups, they're creating individual conclusions, they're using appropriate tools, and what's even better is magnifiers, timers, and balances, and little tools like that, and measuring devices are very inexpensive. So it's not an expensive project, it's very reasonable, anybody can do it, and you're hitting standards that allow them to problem base. So they're classifying, like for instance, they're going to also get into geography. And so like if we did the state of Florida, obviously Florida has more bodies of water. That could be another factor. How could you create the lesson plan to address that as well? You could even, for high school level, make it a little more difficult as well. So, and you can see, for instance, what they're coming up with. There's also an online program in terms of drilling you can use. So once they learn the basics, if you want to go to the high school level, you can get into a computer science program where they actually learn about how industry does it on using the computer and calculating it. So they can compare the two ways, which one's better. So, and looking up the topography of the land, because you know what we do is we go to the Ohio Department, the ODNR website, and we can go to that resource center and we can look up at the land that we want to purchase and figure out approximately what the topography has on it. Because before you purchase the land to say, I'm going to purchase that to drill for oil, you need to know what is in the land to save your money so you don't become a wasteful, independent entrepreneur, as Dr. Grandin Gill is teaching you guys to think for yourselves before you go out and purchase that land. Make sure you know what's on the land so you can use technology. So this is our first grade standards, and you can see measuring length, centimeters, inches, and feet, how we're hitting conversions, because we all know that's very vital for that grade level. And then writing. I mean, writing is so important. We've talked about that as some of us sitting and just discussing every day as professors and teachers and what we're trying to do with our students. You know, this is really important to make our students write and understand and explain. And as they're doing this process of putting this box and these measurements together, you can have them write what they're thinking as they're going along. Because Sarah, my student that was involved in this workshop, very active. They're in Kettering schools, just about 30 miles from Wright State, and they are doing this curriculum, and it's going really well, and they're making their students write as well. And they have found that their state scores have improved, and their students are really thinking for themselves. But that's the good thing. And I agree, some of the state tests are a joke, but at least we see in their classroom that their assessment, they see a pre and a post, that they see an increase within the content knowledge for their students. So that's been very valuable. And so I just want to go on and address a few more content knowledges. Yes, very briefly. I use other techniques like dopamine and dopamine. These are neurotransmitters in the brain. And this was a curriculum I created with Ohio State University. It was called Research Experiences to Enhance Learning. And in that curriculum, what we did was we assessed the content knowledge gains as well using the R.R. Hakey method, because I promised I'd get to that. They had to figure out what type of electrode to detect phenol. And this was in a freshman chemistry level course to detect phenol and water contaminants. You can even do lead and cadmium and heavy metals as well. And briefly, this is cyclic voltammetry, but since we only have 3 minutes and I'm not going to kill you with the chemistry, this is just an SEM. They had to learn about scanning electron microscopy, another technology. They had to learn about Raman Spectroscopy, looking at how to determine polymers versus polymers with lead when they're detecting lead in water. So square wave anodic stripping voltammetry. So what I'm trying to show you is that I'm engaging them into the technology as well, graphing it at a young age. This is a high school student. She is doing an activity in science fair on anti-corrosion, but this year she's looking at neurotransmitter detection with polymers and creating her own electrode. So what I'm trying to do is engage the students to think for themselves, and so far she got a perfect 50 out of 50 just last week at the science fair, so now she'll go on to the state level. So I'm really proud of her because she's really in the process. You can see these students are really working in the lab themselves, engage themselves, learning the new technology. X-ray fluorescence, this is at Bowser-Morner. As I said, we connect with the industry. If we don't have the instrumentation, we don't have SEM, we go to Bowser-Morner. So we take our students to industry, and that way they really get the real experience. Assessment is a vital part. How do you assess your content knowledge, pre and post test? And this is an example of R.R. Hakey. I used this data from the real project, Research Experience to Enhance Learning, and you can see a pre-test score of 15.6%. As our colleague the other day said, oxidation reduction. This was on a concept of oxidation and reduction. And as we take the post-test, we have a 77% increased gain as they had done modules on looking at detecting neurotransmitters of brain and looking at oxidation reduction, the oxidation reduction for the ascorbic acid, and the oxidation reduction for the neurotransmitters detecting with electrochemistry. So starting them at a young age, I think, is vital. And these are our desired outcomes that we hope they will come up as learning abilities, that they will problem solve, effective, and reflect upon the process as they go along. And so I'm not going to bore you with the rest of the slides because they're just other references on the same things I've been talking about. So just briefly, the Chinese proverb is, I hear and I forget, I see and I remember, I do and I understand. In the Chinese proverb, I'd like to say problem-based critical thinking is vital, so that you're making them think through the process and they never forget once they've solved the problem on their own how I feel. And so I've had a really great time at Wright State University working with all these young people, and I hope to continue this process of inquiry-based learning and creating more modules to cause problem-based learning. So I thank you for your time today.